And to be at the IIP in Natal. I hope I can look forward to many more visits. Today I'm going to be, so I'd like to thank the organizers for their very kind invitation to speak. And today I'm going to be speaking on joint work with Alexis Morin-Duchesne, who will join us later, and then Andreas Klumper, who is our illustrious chairman. The topic for my talk today is the analytic calculation of conformal partitions of critical bond percolation on the square lattice. I'll speak mainly about this system on the strip, but really the main interest was the modular invariant partition function on the torus. There's been quite a lot of speculation about exactly what the modular invariant is, and so to settle the question, we decided to do an exact calculation. So you're familiar with the Potts model on the square lattice. You occupy a bond with some probability p. For the square lattice, there's a critical probability for the bond occupation. The model is critical there. I won't work directly with bond percolation. Instead, I'll be working with a dual picture where you work with the surrounding contours. This is a loop model, but it's exactly integrable, and it's really required to describe the conformal properties of this theory, which is a logarithmic theory. So in this picture, you can see we have some input state, we act diagrammatically, and then we have some output state. Here there is one defect. If you trace this through, you see the defect has moved to this position. So let me start by describing percolation as a logarithmic minimal model, and then I'll tell you about its conformal properties. As an integrable model on the square lattice, percolation is a special case of the logarithmic minimal models, which were introduced with my colleagues in 2006. It's a temporally loop model, so basically the faces can take two configurations, which you draw diagrammatically. You can work in a planar temporally algebra. These face weights get weight sine lambda minus u and sine u, trigonometric functions. U is the spectral parameter. Lambda is the crossing parameter, is given in terms of a pair of co-prime integers, p and p prime, and this fixes the model. We're going to be interested particularly in percolation, which is the case p prime equals 2, 3. You can write, instead of working in the planar temporally leap algebra, you can write the local face operators, which add a face to the lattice in terms of the linear representation of the temporally leap algebra, where you have the identity and the generators EJ. 2 cosine lambda is called beta. This plays a special role. This is the loop fugacity. The classical partition function is the sum over all configurations with the weightings for each occurrence of these faces and weighted by the factor beta to the number of loops. This is a non-local model. There are no local degrees of freedom, no spins, no heights here, only extended non-local loop segments, which are connectivities. So you need to work diagrammatically with these models. For p prime equal to 2, 3, the crossing parameter is just pi on 3. The isotropic point is when u is equal to lambda on 2, which is pi on 6. On a strip, we need to specify boundary conditions on the left and the right. We specify a Hilbert space of states that we act on, and then we act diagrammatically on some in state to produce an out link state. The link states are connectivities, planar connectivities between the nodes at the top edge here. So here this is the in state, and this one is the out state. You see the defect has moved to this point here. In 1980, Keston showed that the percolation, bond percolation on the square lattice is critical at the critical threshold PC, which is 1/2, and at the isotropic point, both of these weights become exactly 1/2. The loop version of percolation goes back to Duplantier in 1988. Sometimes it's referred to as Hull percolation. There's a one-to-one mapping between configurations of the red bonds, that's the bonds of the usual percolation model, and the configurations of the surrounding contours, the loops. When lambda is equal to pi on 3, for percolation, the loop fugacity becomes 1. So whenever you have a closed loop like this one, it is assigned a loop fugacity weighting, which is beta, but for percolation, beta is just 1, so the factors of beta to the number of loops effectively disappear, and in this case, the model is stochastic. As a CFT, in the continuum scaling limit, this loop model of percolation is a logarithmic CFT. And the central charge is given by the usual Katz formula. You just put P and P prime equal to 2 and 3, and you get the central charge 0. The conformal weight delta 1, 1 is 0. Similarly, you can look at the Katz formula, and you can set up an infinitely extended Katz table, where you now just allow the Katz labels R and S to be integers, rather than restricted to a finite set, which is the case for the minimal models. These models are called logarithmic minimal models because in general, for each minimal model, say 4, 5 or 2, 5, there is a logarithmic counterpart. So you can have a logarithmic tricritical easing model, a logarithmic Li-Yang model, but the logarithmic minimal model 2, 3 has no rational counterpart. The rational counterpart sits in the bottom left-hand corner here. It has just 2 conformal weights, 0. Effectively, the model is completely frozen. That's why you need to work with loops to describe the CFT properties of percolation. For each conformal weight, there is a character. Here are these Katz characters. You can obtain them as limits of the rational minimal Katz-Virasoro characters by taking m and m prime in your model both to infinity. R and S are the Katz labels. On the lattice, R is not a good quantum number, but S is. On the strip, S is related to the number of defects. And on the cylinder, S is related to the number of defects divided by 2. And formally, you just allow S in these formulas to be half integer, and you get a lot of values in between the values shown here. Next, let me describe the integrability, quantum chains, and transfer tangles for these models. Because this is a temporally Lieb model, it's automatic that it's integrable. To see that, we fix the rational parameter, crossing parameter. So this is a simple fraction. So we're looking at the case of root of unity here. The relations in the temporally Lieb algebra are just these. Ej squared equals beta Ej. This product of 3 Ej's gives back Ej. And if Ej and Ek are separated by a distance greater than 1, then they commute. As I said, the face operators can be formed diagrammatically or in terms of the temporally Lieb generators in the linear algebra. It's very easy to show that these face operators satisfy the local inversion relation. So a product of 2 faces gives the identity up to some scalar factor. And then we have the famous Yang-Baxter equation being satisfied as well. With these 2 relations, it's straightforward using the diagrammatic methods of Baxter to show that you have commuting transfer matrices, a commuting family in the spectral parameter U, and this is the essence of integrability. We will need to work diagrammatically, so it's nice to interpret the temporally Lieb algebra diagrammatically. And let's start on the strip. Here are the 2 generators diagrammatically. This is the identity. The connectivities just flow through upwards. But here's something interesting happens. This is a monoid diagram. And corresponding to the loop fugacity, whenever you get a closed loop, you assign it a weight beta, which is just 1 for percolation. The usual defining relations of the temporally Lieb algebra can then be shown diagrammatically. If you multiply 2 monoids together, Ej by Ej, you identify across the gap. These points are identified. You form a closed loop. It gets pulled out. It's a scalar factor assigned the weight beta. And then you collapse the diagram, remove the middle portion. You see you get a single Ej generator back again. Likewise for Ej, Ej plus 1 Ej. You follow the connectivities. Only the connectivities are important. You see this point is connected to this point, so that becomes a straight line. And we have this connectivity here and here. So we get back a single Ej. Of course, these are local relations. Outside of these 3 positions here, everything acts as the identity, which means you just have a lot of vertical strings. And we're using properties of isotopy, which only hold for critical models. This is a conference on quantum chains, so let me describe the quantum Hamiltonian. If you take the double row transfer matrix, which I showed earlier, diagrammatically, it's just here. It's formed by a product of two faces of the two rows of the lattice with spectral parameter u at the bottom, lambda minus u at the top. If you take the logarithmic derivative of that object, then set the spectral parameter equal to 0, you find that the quantum chain associated with percolation and the logarithmic minimal models in general is just the sum of the EJs, and often it's convenient to introduce a shift. This is actually a very interesting quantum chain in its own right. It's called the Raisin-Peel model. It was introduced by myself and colleagues, Jan de Geer, Bernardine House, and Vladimir Rittenberg. It's a Markov matrix and is actually a model of a conformal stochastic process of a fluctuating 1D interface. So this has been studied extensively by Francisco Alcaraz and Vladimir Rittenberg. For a periodic system, you have the shift operator, where the connectivities just shift one space to the right or one space to the left, so you have more relations in your extended or enlarged temporally Lieb algebra. The relations are here, and the most important one is this one. So this one tells you that when you have a non-contractible loop, the weight of the non-contractible loop is alpha. So here's an example here. You can see when I multiply these two together diagrammatically, there is a non-contractible loop that goes all the way from the left to the right. And now we have periodic boundary conditions. So this particular product, we have one factor of alpha that we pick up when we pull this one out, and when we pull out the closed loop, we get one factor beta, and then you look at the connectivities at the top and the bottom, and you get this diagram. So again, all the multiplication in this enlarged temporally Lieb algebra is exactly what you'd expect just by drawing diagrams. Again, you can now work with a single row transfer matrix, call that T rather than D for a double row transfer matrix. Take the logarithmic derivative, set u equal to 0. You get back the expression for the quantum chain Hamiltonian expressed into the EJs, and again there is a shift for convenience. So essentially we're studying these two quantum chains, two different topologies, the strip and the cylinder or torus. Now the way the logarithmic minimal models are set up, they really are quantum models. You have to specify the Hilbert space of states that you act on before the model is completely specified. And here we're going to act on standard modules of link states on the strip. Here are the planar diagrams that you can form by connecting pairs of nodes in a planar fashion so that the arcs don't cross, and allowing for a specified number of defects. Here I've specified 2 defects with a system size of 6, and these are all the diagrams. Here is the counting of these states, and this is the basis for the Hilbert space. And then when you must act in a way that preserves the quantum number d, which is related to the Katz label S. So in this case, you act diagrammatically, you go from this state to this state. Here you act diagrammatically, you go from this state to this state because you form a closed loop with weight beta. And here, the in state has 2 defects and the out state would have none, so that's not allowed, so this is set to 0. You do exactly the same thing for the periodic situation, only now we have periodic link states, so now the arcs can close to the left or to the right around the back of the period, so we have to keep track of that. And here's the example with d equal to 1 defect, and 5 nodes, and this is the number of link states you get, and the dimension this time is given by a simple binomial. Again, the action must preserve the number of defects. So in this case, you can see with the action here, I generate a non-contractible loop, so it gets weight alpha, and the out state is just 2 simple arcs. Here I act on a link state with 2 defects, but the out state has no defects, so that's set to 0. And now comes some complication. Excuse me. Now there is some slight complication. Here, when I act, I form a closed loop on this boundary, so that picks up a factor beta. But now these defects are moving, so I introduce a winding parameter omega that keeps track of the winding of these defects. And over here, you can see that they're winding, but in the opposite direction. Ultimately, I will set the non-contractible loop fugacity to be twice cosine gamma. And I will set omega equal to e to the I gamma, that's the winding parameter. And we will take gamma to 0, so that ultimately alpha will become 2 and omega will become 1. This is the only situation that will be of interest to us ultimately. We need to set up the transfer matrices, and for percolation there are 2 transfer matrices that are relevant. Let's start on the strip. There is the fundamental double row transfer matrix, which has the simplest possible boundary conditions. You just close arcs on the left and the right. Here is the lower row with spectral parameter u and the upper row with spectral parameter lambda minus u. We use a convenient normalization that will not affect the conformal properties. When you fuse this object, you form a higher level fusion or fused double row transfer matrix. That's D superscript 2. And these are formed by 1 by 2 faces, u on the bottom, now minus u on the top, and now we close double arcs because it's fused on the left and the right. So the fused 1 by 2 face weights needed to construct this commuting transfer matrix look like this. 1 by 2, you have u at the bottom, u plus lambda at the top, and then you act with projectors on the left and the right, and we normalize, and the projector is just the sum of the identity and the Template-Lieb generator acting in the horizontal direction. So when you put these 2 diagrams in for these projectors, it decomposes into these 2 diagrams, and everything has trigonometric weights, where the trigonometric function SKU is just sine u plus k lambda on sine lambda. So these are constructed so that they are mutually commuting. Similarly, for the periodic situation, we have a fundamental transformation which we denote by T1. That's the usual transfer matrix. We use a normalization I to the n now. The spectral parameter is just u, and now we have periodic boundary conditions, and the system size is n. And now we can form the fused object, where we just replace these weights with their 1 by 2 counterparts, and we get the T2 higher level fused single row transfer matrix, and now a convenient weight is minus 1 to the n. Now on the strip, at some point we're going to need to close the strip to form a cylinder. To do that, you just use the usual matrix naive trace. That doesn't work when you want to close the cylinder to form a torus. To do that job, you need to use a modified trace, which I introduced with my colleagues in 2013. It's like a modified Markov trace. And when you use that trace, you have to weight the various sectors appropriately. And this is the appropriate object to look at for the torus partition function when you close the cylinder to the torus. So we'll need to calculate with this later. All right, next let me move on to T systems, Y systems, TBA, and physical combinatorics. We start with the fundamental. Now I'm going to work with the periodic system. Everything works similarly for the strip, except there are some order 1 terms. In the setting of the minimal models, it was shown by Bajanov and Reshetikhin that these fused transfer matrices satisfy fusion hierarchies. So these T to the N are mutually commuting higher level transfer matrices. And the form for the logarithmic minimal models is essentially the same. And here are the initial conditions, and there is some extra relationship here. These F's are just powers of n of the same trigonometric functions that we were dealing with before. But what is interesting is these relations generalize to the logarithmic minimal models, and then there is a closure. And here are the closure relations. So you go out to level p prime, and then it closes back on previous levels. T0 is just defined. Where is T0 defined? Here, right. Sigma is just I to this power, and J is related to the braid matrix and is related to the winding parameter. That's annoying. It's related to the winding parameter omega in this way. So these closure relations are very nice and enable you to work with these equations. Yeah, sorry, hi. Yeah, it's exactly the same T2, but in general for the P prime models, you have all of these different higher level fusions going up to P prime, and then it closes. For the model percolation, P prime is equal to 3. So you have 1 and 2 are independent, and 3 you already had the closure relation. That's the difference between the general situation and the specific situation we're interested in here. So on the strip, exactly the same equations hold, but there are order 1 terms floating around everywhere, which makes it look ugly, so I won't write down these equations. From the fusion hierarchy, it's known since '92 that you can go to the so-called T-system, and here are the T-system equations. And again, they hold in the rational setting, studied by Andreas and myself in '92, and in the logarithmic setting. The Y-system uses ratios of T's, or in this case, a product of T's divided by some F's. These little T's are, in fact, the going to be the Y's. So here is the T system. You introduce these little t's, and then you get the Y system. The nice thing about the Y system is that these objects are universal and connect with the conformal description through finite size corrections. In the logarithmic minimal setting, then we have these same Y systems, but now we can use closure relations, and the closure relations take this form, where K0 is simply related to the last higher level Y or little t here in this chain of Y system equations. Notice that on the right hand side we have these complex exponentials. J is the cosine of this lambda, and it's related to Chebyshev polynomials in the braid limit of the transfer matrix. So these are just some objects that enter these equations. Now when you look at the structure of this universal Y system, you see that you're just moving along a chain, but then because of the closure at the end you get a branch point. So we're working with a Y system on a D-type Dinkin diagram, and for P prime equal to 3, that's percolation. This collapses to just 3 nodes, which take this form. You could say this is A3 because it's just a linear chain, but because it's a collapsing of a D diagram, we just call it D3. And notice that the symmetry between the two end nodes is broken because there's a plus I lambda here and a minus I lambda there. So they come in with in a different way. So from this, for bond percolation, we have a rather simple Y system after using closure. There is this equation and this equation. So this equation applies to this node, and then this one closes at the endpoints. Here I've discussed the periodic system, but exactly the same Y system holds on the strip, and in that case this lambda is 0, so the distinction between the two end nodes disappears. The situation is somewhat simpler because of universality. All of the order 1 terms coming from the boundary contributions cancel out, and you get the same universal Y system. From the Y system, you can go to a thermodynamic beta ansatz equation. So the universal Y system for percolation can be written in this form. There are just two equations. This is the first one, and this is the second. I'm on the cylinder, so I have plus or minus I lambda here, and these Euler factor A's are just related to the original transfer matrices T2 and T1 with some trigonometric functions which enter here. This is a standard form for a TBA equation, and so you can convert these functional equations to nonlinear integral equations. This is a standard technique, and these equations become this if you're looking just at the ground state. And here I'm rooting it down for the ground state in the sector with no defects. So K is the kernel of this integral equation, and we have the usual convolution. Once you have a standard TBA like this, there are standard methods using dialogarithm techniques to calculate the conformal weights in the different sectors. I've only written down the sector with d equal to 0. And when you use those standard methods using finite size corrections, what you find is that the logarithm of the eigenvalues of the single row transfer matrix take the expected form. You have a bulk contribution. There's no boundary contribution here. The 1 on n finite size corrections are related to the conformal properties of the model, and then there are higher corrections. And indeed what we find is the central charge here, C, turns out to be 0, and delta equals delta bar is minus 1 on 24 for the ground state of the d equals 0 sector. More generally, using dialogarithms, we find that delta equals delta bar is delta 0 with S. So R is set to 0 and S is set to d on 2 in the Katz formula. That gives you d squared minus 1 on 24, which takes these values. And we're going to focus on the first column where you get the weights 0 and 1/3 and integer tower above those two. Again, similar equations hold on the strip with one copy of Virasoro. And in that case, the upper and the lower half planes are related via complex conjugation symmetry, and your life is somewhat simpler because this lambda here is just 0. Now I said we need to use some dialogarithm techniques, and so when you are solving the TBA using these techniques, you have to evaluate some dialogarithm integrals, and in this case the dialogarithm integrals that enter all of this form. So sigma can be plus or minus 1, the argument gamma for percolation is 0 or 2 pi on 3, but we allow it to be arbitrary, and these three dialogarithmic integrals are entered here, and they're related to certain asymptotics of the transfer matrices in the analyticity strips. For a gamut between 0 and pi, we can actually evaluate these integrals, and they're given in nice closed form expressions as quadratics in gamma. And then we can specialize to the points of interest, gamma equals 0 and 2 pi on 3. And when you do so, you find that the fractional part of the conformal weights in the first column of the Katz table, which starts off as 0, 0, and then 1/3, are indeed 0 and 1/3. So these are the only dialogarithm identities that are needed to obtain the finite size corrections, the conformal weights, and even all of the excitation spectra in the first column of the Katz table, and that's the only column we look at. We don't look at r greater than 1 in this work. Solving TBA equations is a lot of work, but by now it's quite standard. We want to move on and look at the spectrum of excitations. We want to obtain the characters, which are of this form. The DEs are degeneracies, Q is the modular parameter, E is the conformal energy, and so on. These are the generating functions for the eigenenergies E of the quantum chain. So the calculations proceed, as I say, by completely standard methods. And you have to look at the analyticity strips in the complex U-plane. You have to look at braid limits and bulk asymptotic limits. You need excitation numbers of quantum numbers which come out. There's a lot of information that you need that goes into the solution for the excitations. But most importantly, you need an understanding of the patterns of the zeros of the eigenvalues in the complex U-plane and their selection rules. So the exact location of the zeros is not needed in this way of solving the system, but you do need the relative ordering of 1 strings and 2 strings in the analyticity strips. So this information has to be obtained empirically. So that's the most difficult part. We find these patterns of zeros and selection rules empirically, and that reduces to a combinatorial problem. So now we have a big combinatorial problem to understand the analytic structure of the eigenvalues of the transfer matrices. And this problem is solved by using Q binomials and Skew binomials, which I will now explain. So Q binomials are probably familiar to most of you. It's just m plus n choose m. You can write it this way in terms of excitation quantum numbers. Here they are written in terms of Q factorials. But it's much better to think of these objects diagrammatically as single column diagrams. So when a pattern, if you directly diagonalize the transfer matrices, they're commuting transfer matrices, so you can get the eigenvalue as a Laurent polynomial in the e to the iu. You can then put it on a computer and you can see zeros precisely in the complex U-plane. You immediately identify analyticity strips. And what you see in an analyticity strip shaded blue, we're only working in the upper half plane here. I'm looking at the strips, so the upper and lower half planes will be identical. Is you see these patterns of 1 strings shown in red and 2 strings shown in green. And this is the ground state in this sector. We're looking at 4 choose 2. And this is assigned weight 1, and then each time you interchange 1 string with a 2 string, that is, you gradually promote these 2 strings, you increase the excitation energy by 1. And if you exhaust all possibilities, you generate these 6 diagrams, and that indeed generates for you then the expression for the Q binomial. So you can recognize the Q binomials just by looking at output from a computer for a finite system of the structure of the eigenvalues. These Q binomials are realized as sums of Young or Maya diagrams, whichever you prefer, and these diagrams inside a box are just weighted by the number of small boxes, 0, 1, 2, 3, and 4. So these are naturally related to partitions and all sorts of things that excite pure mathematicians. We will also need skew Q binomials, and these are related to double row diagrams. And these were introduced in the study of critical dense polymers, which is the logarithmic minimal model 1-2 in 2007. And these Q binomials are given as differences of products of 2 ordinary Q binomials. Again, they have a nice diagrammatic interpretation. You have an analyticity strip. We're only looking at the upper half plane. Now at each position in the center of the strip, you can have a double 0, a single 0, or no 0. The number of 2 strings is complementary. So if you have 2 1 strings, you have no 2 strings. If you have 1 1 string, you have 1 2 string. And if you have no 1 string in the center, then you have a double 2 string. So this diagram refers to this first of this grouping. These diagrams always come in these groups. In the lower position, this double 0 in the middle of the strip is represented by the 2 zeros or dots here. This one is a single one, it's here, and then at the top there are no 1 strings, so we have no here. So double, single, 2. And the rules of the game is that you generate all the diagrams. We have 1 0 on the left, 2 on the right out of 3 positions. So that's this m choose mn skew Q binomial. And if you start at the top, you can draw diagonal slopes. So this one connects to the top one, which is here. This one is left over, it doesn't connect to anyone. This one connects here, this one connects to that one. Each of these slopes shown in red must have a positive slope. That's what defines these skew diagrams. The skew diagrams are also related to partitions, but skew partitions. So I don't want to make a big deal of it, but you can write these as sums over skew partitions, and now you get basically two Young diagrams, and the weighting is the is a q minus 2 here, then this one gets a weighting 2, and now the shaded boxes get a weighted 2, so this is 2 plus 1, that's 3, this is 3, and so on. So each of these can be represented as sums over weighted skew partitions. So these are very natural objects. All right, let me move on to part 4. We want to look at the strip conformal partition functions, and these will generate for us the finitized characters. So when you look using a computer for a finite size, here I'm looking at finite size n equal to 8, and I'm setting d equal to 2, so 2 defects. That means that the Katz label S takes a value d plus 1, which is 3, and delta 1, 3 is 1/3. And now I've listed off all of the 28 patterns that we see on a computer. And these patterns all fall into groups described by the single row diagrams and the double row diagrams. And excuse me, sorry, that happens all the time. There is quantum numbers associated with these. So you can see the single one occurs at position 1. Here the single zeros occur at positions 1, 2, and 3, and so on. So there's all these quantum numbers. These are for the single row column diagram on the left, and there's a double row column on the right. There's a 1 and a 1, and so on. And each one of these is associated with an eigenvalue, and here I've listed off the conformal energy starting with 1/3. That's the sector rule we're in, and then you increase in steps of 1, and of course you build up degeneracies as you go. And you need to classify all the patterns and understand why and where they occur, and this is what we find. We just get a union over products of the various allowed single and double row columns, and it completely accounts for all of these eigenvalues, and similarly for larger sizes, so we can be quite confident that we've really understood the structure of the zeros for these patterns. And this is important because you have to remove these zeros when you solve the TBA equations, because there you can only work with A and Z, analytic non-zero functions. So these actually have to be removed by hand in the calculation. For percolation, we're just looking at the D3 Dinkin diagram. Here are the two functional equations. In this case, there are two analyticity strips that are relevant. The first one is related to D1. This is the equation on the strip. So we're working with double row transfer matrices, so little d instead of little t. That's this node here. And then there are the nodes 2 and 3, which are associated with k. So we have now a very simple Y system. Two analyticity strips, as we saw, and we have 1 strings and 2 strings. We have done the combinatorial classification of the patterns of zeros. We can now go ahead and solve the TBA equations. And when you do so, this is what comes out. So now here are the contributions of the double row diagrams. Here are the single row diagrams. The double row diagrams are associated with this node, which is the branching point. The single row diagrams are associated with the end point. And you have to take the products of those, and they come in weighted of q to some quadratic. There's a leading power of q. And you see that this is a fermion expression. Everything comes in with positive coefficients. But from the initial work with Rasmussen and Zubair in 2006, we obtained the expression for these finitized characters as this simple subtraction here. This is bosonic because you introduce positive coefficients and then you have to cancel some out. So now we have an alternative refined expression for the finitized characters, but somehow these have to be equal. It's easily checked that when n goes to infinity, these indeed reproduce the Katz characters of the logarithmic minimal models, in particular the case of percolation. So this is the case when S, which is d plus 1, is 3t plus 3. And you find similar expressions for the other cases when S is equal to 1 or 2 mod 3. In general, for the logarithmic minimal model, the branching node is associated with skew binomials, and all the other nodes are associated with regular Q binomials in single row columns. The skew binomials are different to products of two binomials, so to prove this identity here, we have to somehow replace this with a product of two binomials and subtract the other one. And so we have to work with sums of products of three binomials, and we have to first remove one of the sum, leaving a sum of products over two Q binomials, and that last sum we can perform using the Q Vandermonde identity. So here is the identity. It's quite horrific. We managed to come up with this elementary proof, but then after our paper was published, Olivana pointed out to me that actually this is just the Q Salschutz identity. This is quite a famous identity from all things Q, and goes back to Jackson in 1910. So this is classical mathematics. And the proof that we came up with is actually very close to an elementary proof given by Gould in 1972. So it's very interesting that these high-powered identities from Q number theory come into the solution of these logarithmic minimal models. Now let's move in the last part to the modular invariant partition function on the torus. We have to repeat these calculations, but on the torus. And the essential feature that is different on the torus is that the patterns of zeros are different in the upper and lower half plane. We no longer have complex conjugation symmetry. So here are the 20 patterns of zeros that occur in the standard module for n equal to 6 with no defects on the cylinder, and we should get delta 0, 0 because delta bar 0, 0 is minus 1 on 24. And I didn't list all the quantum numbers, but just the contributions from the upper and lower half plane. They contribute separately. So we have to understand the patterns of zeros and classify them in the upper and lower half plane and combine them to form the sesquilinear partition function. And here it is for n equals 6, d equals 0. You just add all of these together. We completely understand this classification. We can do everything again in terms of Q binomials and skew Q binomials. This time we have to use the modified trace, and then the modular invariant partition function should come out in the limit as n goes to infinity. I won't go through the details. The original paper is 70 pages long. There's a lot of technicalities, but a similar analysis generalizes to the single row periodic transformatrix on the cylinder. And what comes out is this modular invariant partition function. You can see it's a sesquilinear form in characters, but these are not the cat's characters. These are specialized affine U1 characters. The other surprise is that this is not an A-type modular invariant. You might expect these models to have a simple A-type modular invariant, but actually this is D-type. So you can see 1 and 5 come in this way. It's not a simple square of the character 1 squared and plus the character 5 squared. It comes in as non-diagonal, that is D-type. Q here is the modular norm. It's related to the aspect ratio of the lattice system. Actually, you can understand the structure of this modular invariant is related to the bosonic, the simple bosonic partition function, and you can understand the structure in terms of these diagrams involving the twisted A2 with a product with a twisted A3. So this is twisted A2 Dinkin diagram, twisted A3 Dinkin diagram. We live on one sublattice, and you get this graph, which is intimately connected with the properties of percolation. And you can see on the outside, everybody appears as singletons, 0, 2, 3, 4, and 6. But on the inside, we have 1 and 5. So on the outside, everyone is their own Bezout conjugate, whereas in the inside, 1 and 5 are Bezout conjugates, they're not self-conjugate, and that explains why you get this term here and this term here. So this is, in a sense, the Katz table, and here are the conformal dimensions associated with these positions in now the U1 Katz table. So when you go to the torus, somehow a higher symmetry emerges that you don't see when you're on the strip and you have boundary conditions that break the translational invariance. A simple identity gives a trivial Virasoro character. This is the Virasoro 1, which is just 1. As I told you, M23, the minimal model, is a trivial model. It only has the identity operator, and this is related to the difference of chi1 and chi5. Thank you. So I'm right on time. So let me finish by summarizing what we've seen. We've seen the critical bond percolation on the square lattice is just the LM23 logarithmic minimal model, the first in an infinite series of exactly solvable models describing log CFTs. The universal conformal spectra is obtained analytically. We solve the Y system on the strip and we get the expected results given by the Katz formula, namely C equals 0 and the conformal weights given by this expression. Here S is an integer, but more generally it can be a half integer. The finitized conformal characters have been obtained, and we showed by a large identity that actually they're equivalent to the ones given in the original paper with Rasmussen and Zuber in 2006. Solving the Y system on the torus, we found a D-type U1 modular invariant partition function, and it's encoded by twisted affine coset graph. The Z2 is just the simple quotient on the two sublattices. But there are some remaining open problems. We only looked at the case R equal to 1, corresponding to the first column of the Katz table. It would be very interesting to look at the general RS-type Katz boundary conditions, which are all known, and to reproduce the finitized characters in that situation. Similarly, there are known Robin boundary conditions which lead to half-integer values for the Katz labels R and S, and it would be interesting to look at those boundary conditions as well and solve the TBA equations and so on. We only looked at the case P prime equal to 2, 3, corresponding to percolation. That's just one of the smallest examples beyond critical dense polymers where everything is known quite explicitly. That's the case P prime equals 1, 2. But based on 1, 2, and 2, 3, it's a natural conjecture to say that the modular invariant partition function should take this form, where omega 0 j here is just the Bezout conjugate of j. And this you'll recognize, hopefully, as the modular invariant partition function of a boson on the circle C1 with this particular radius of compactification, and the effective central charge is C effective equals 1. Actually, all of these logarithmic minimal models have the C effective equal to 1. However, the combinatorial description and the analysis of the TBA, D-type TBA for these general systems looks quite formidable. So with that, I thank you for your attention.